Hello, welcome back to Mech 416/816 Engineering Acoustics. In this video, we're going to continue discussing the 1D elastic wave equation, and we're specifically going to focus on the solution by the method of separation of variables, which will lead to what are known as normal modes or modes of vibration, or also eigenvalues and eigenfunctions. We're going to start by considering the general wave equation. In this case, we're going to say that B times X times u tt is equal to the quantity A of x times u sub x, all of that sub x, plus some forcing term f of x comma t, valid for 0 less than or equal to x, less than or equal to L, and t greater or equal to 0. With boundary conditions, we're just going to consider simple boundary conditions in this example or in this derivation. We can go over non-simple boundary conditions in class. So we'll just do fixed boundary conditions in this case, both of those equal to 0. And then with generic initial conditions, u of x comma 0 equals function h of x, and u sub t of x comma 0 equal to a function g of x. Okay, so a natural approach is to seek solutions that are separable in time and space. That means we want to try and separate out what happens in time from what happens in space and try and produce an equation for time, one for space, and then solve each of those equations separately and then bring those back together later on. So what that implies is that we want to seek a solution of the form u of x comma t is equal to some function phi of x times a function psi of t. And here we're going to now ignore f of x comma t, and we're going to focus, then substitute equation 45 into equation 42. This is going to produce the following. We'll get b of x times phi of x times psi double dot of t is equal to the quantity A of x times phi prime of x times psi of t, all of that to an x. Again, we're ignoring the force here, so that we'll leave it like that. We're going to also set b equal to b, a constant, and a equal to constant a. That would just simplify it, and in this class we won't have to deal with any spatially varying mass distribution or tension or elastic modulus or areas. Okay, so in that case we then end up with the following. We end up with b times phi, should be phi times psi double dot, which is then equal to a times phi double prime times psi. If we divide by b, we can then get phi psi double dot is equal to c squared phi prime double prime times psi, where here c squared is equal to a divided by b. At this stage, we're then going to divide both sides of that equation by phi times psi. So we get phi over psi double dot divided by phi times psi is equal to c squared phi double prime psi divided by phi psi. And we can end up eliminating a phi on the left and end up eliminating a psi on the right, such that we have psi double dot over psi is equal to c squared phi double prime over phi. And something special happens here. On the right hand side we have a function of time only, and on the left hand side we have a function of space only. So whenever you have two functions that are equal, that have different independent variables, which is the case here, they have to be equal to a constant. That's the only way this can be true. And it could be any constant, but we're going to be smart, and we're going to say that this constant is minus lambda squared. This then leads to two equations. It leads to, first, an equation for the evolution of the behavior in time, and then second, one for the behavior in space. So first, let's just deal with the time. So we have psi double dot over psi is equal to minus lambda squared. This gives us the following second order differential equation: psi double dot plus lambda squared psi is equal to 0. And then secondly, we start with phi double prime. Actually, it should be c squared phi double prime over phi is equal to minus lambda squared. This then leads to the equation phi double prime plus lambda squared over c squared phi equal to 0. So let me switch colors here. Here you can use initial conditions if you wanted to solve that. We won't deal with that, but instead we're going to focus on only the space part. Here we're going to need boundary conditions. And to be more specific, here you would need to recast them. Let's just rewrite this whole thing. Here, we're going to have to recast our ICs into, not into, but using psi. And here we have to recast the boundary conditions. Using phi. There. Okay, so let's briefly do that. Okay, so at x equals 0, we had u of 0 comma t is equal to 0. This must be equal to phi of 0 times psi of t. What this tells us then, since psi of t can't be 0 for all time, then phi of 0 must be equal to 0. Similarly, at x equals L, we have u of L comma t is equal to 0, is equal to phi of L times psi of t. Since psi of t can't be 0 for all time, we get that phi of L must be equal to 0. So from here, we get the following differential equation. We have phi double prime plus lambda. Let me rewrite my lambda squared over c squared, phi equals 0, with the conditions phi of 0 equals phi of L, and both of those are equal to 0. I'm going to move my boundary conditions down, move that over, and that's our equation 50. Okay. In fact, let's move these down to 51. So 51 plus the boundary conditions. Okay, so the solution to that differential equation is going to be something we've seen before. We solved the second order differential equation when we studied the harmonic oscillator behavior. And here we're going to need to solve it again. In fact, this second order differential equation is something you're going to see repeatedly through this class. So you should learn how to solve these now, because it will pop up many times in the future. We will be dealing with this again when we solve the acoustic wave equation, when we deal with other topics in pipes and so forth. So it's important that you know how to solve this. So phi of x, and in fact this is important enough that it's worth making it a mini homework. So this will be mini homework 4. let's make this due on, February 15th. Or if you want to turn this in with mini homework 3 on the 13th, that's fine too. This will again be 5 points. And I want you to solve the ODE given by equation 51. That is, I want you to show the steps to produce the solution that I'm about to write down in equation 52. So the solution to that differential equation is phi of x is equal to c1 times the sine of lambda over c x plus c2, some constant c2, times the cosine of lambda over cx. So what I want you to do in the mini homework is to show the steps that takes you from equation 51. I'm going to rewrite this. Let's just say that what I want you to do is show that the solution to equation 51 is equation 52. I want you to show that work. And again, this is something that you should try to solve and get used to solving because you're going to see it repeatedly throughout this class. Okay, so from here, we're going to apply the boundary conditions to try and find the constants and lambda. We have 3 unknowns, lambda and the 2 c's. However, we only have 2 boundary conditions. So what that means is that we will be left without being able to solve for one of the c's. We're going to have to find one of those constants, and we'll also be able to find what lambda is. Okay, so we're going to start by applying the boundary condition at x equals 0. You should always start by applying the boundary condition at x equals 0, because it is usually the simplest. So phi of 0 is equal to c1 times the sine of 0 plus c2 times the cosine of 0. So the sine of 0 goes to 0, cosine of 0 goes to 1. This is equal to 0, and so therefore we find that c2 is equal to 0. So the reason you always want to do this, always want to start with x equals 0, is that you tend to end up eliminating one of the constants, especially if it is a simple boundary condition. So let's just add a note here. Always apply boundary condition at x equals 0 first. There are times where it's more convenient to apply a boundary condition at x equals L. And typically in those situations, you will reformulate the system such that the independent variable is x minus L, or L minus x, rather than being dependent on x itself. You will end up recasting the solution 52 in the form of L minus x, so you would have cosine of lambda over c times the quantity L minus x, or x minus L. You end up recasting in that form such that you can eliminate something there. However, as a first step, you should always apply the boundary condition at x equals 0 first. This will usually allow you to eliminate something. If not, then you can try recasting that equation 52. Okay, so we now have found that c2 is equal to 0, and that then tells us that phi of x is only going to be equal to c1 times the sine of lambda over cx. And you see we've now lost that cosine term, which greatly simplifies the derivative at L. Okay, so now we're going to apply the next boundary condition, which is phi of L is equal to 0, which is equal to c1 times the sine of lambda over CL. And in this case, we cannot eliminate that sine term. We actually have two options in terms of a solution here. So let's write it here. So we will either have that C1 is equal to 0, or that the sine of lambda over CL, not x, that is equal to 0. This first solution, the C1 equals 0, this is our trivial solution, meaning that it's not interesting and we don't want to do that, which leaves us only the sine. That's the one we're going to choose. So I wrote it here. We're going to choose that the sine of lambda over CL, that must be equal to 0. Which will then allow us to find lambda. So in this case, we can take the inverse or the arc sine. So we get lambda over CL is equal to the inverse sine of 0, which is equal to n pi, where n is equal to 0, comma 1. Actually, in this case, it's not 0. It's just going to be 1, comma 2, comma 3, comma dot, dot, dot. That 0 term will only show up when you have free boundary conditions. If you have any fixed boundary conditions or a spring or a mass or something, then you won't have n equals 0 as a valid solution. Okay, so we can now solve for lambda, and we find that lambda must be equal to n pi times c divided by L, where n here is equal to 1, 2, 3, dot, dot, dot. So what this now tells us is that, first of all, lambda has infinite values, so we can say lambda n instead, and that means that phi also has infinite solutions. So let's say here that phi n of x is equal to some constant Cn times the sine of n pi divided by L times x. That's one of the solutions, and this is true for n equals 1, 2, 3, on to infinity. Okay. So let's now talk about what the normal modes of vibration are. What we found by solving for phi is what we can call the eigenfunctions, or the mode shapes of the vibration. So a normal mode consists of both a mode shape or an eigenfunction, as well as a natural frequency, which ends up being related to the eigenvalues as well. In this case, the normal mode of vibration is going to be the following. It is going to be a set of natural frequencies, omega sub n, equal to n pi c over L, and a mode shape or eigenfunctions phi n of x equal to that constant Cn times the sine of n pi over L times x. And then this is true for n equals 1, 2, 3, and so on. And so n equals 1 gives you the first mode, gives you that first natural frequency and first mode shape or first eigenfunction. N equals 2 gives you the second natural frequency and the second mode shape, and so on. And so just to be absolutely explicit, these are our natural frequencies. And these are our mode shapes. Or also called eigenfunctions. Those two are used interchangeably. So when someone asks you to solve for the modes of vibration, you're finding the natural frequencies and the mode shapes or the eigenfunctions. Another thing I want to point out is that in the single degree freedom oscillator, we only had a single natural frequency. Here we have an infinite number of natural frequencies that occur at multiples of n pi c over L. Multiples of pi c over L. And so all the ideas of resonance, where you can have an infinite response, etc., all of those ideas apply here as well for each of these modes. And so the ideas that we studied with resonance and also with like mechanical impedance, those ideas transfer over here as well.